The next one, that would be the linear programming problem. So we still have a cost function, a scalar function, that is, we have x, that is, in n-dimensional space, we have n decision variables, and this function is defined like this. It's just different from the least square problem. Why we call this is the linear programming problem? Because everything is linear. The cost function, that is C transpose times X. If you are going to look at this C, that is a column vector. If you are going to apply the transpose right here, it becomes a row vector. So C1, C2 up to Cn, they are constants. And then we have to find out what these constants are, because they are defined by the application. And then the unknown right here, that is the decision variables, we are going to adjust the value of x so that we are going to minimize this cost, and subject to some constraint. And then the same right here, note that this ai, that is not the column vector of the a in the previous problem. Yeah, so this a, that is, represents some constant right here, and then this is a constraint. A transpose T x less than bi. Bi is a constant as well. So this is a constrained optimization problem, and bi sometimes that is called the boundary. I mentioned about less than or equal to right here, but actually in some cases we can accept equality constraint as well. Yeah. So again, C, A, and B, they are constant defined by the problem. The only unknown, that is x, we would like to find out what value of x that could minimize the scalar function f, so that subject to all these constraints. So these are the steps in solving the linear programming problem. We are going to, the first step, that is, we are going to formulate the problem. That is, we would like to find out what the decision variable it is. So we have the vector. What would be x1 represent, x2 represent, and so on, and how many of them, and then describe the function, the objective cost, or the fitless function, that is the f of x. It is a scalar function. It will return you a single value if you fit in x into this cost function. And then we are going to have the constraint as well, a I t x less than bi. Yeah. So once we define the problem like this, and then we are going to graph the constraint. Yeah, because we can use the computer program as well, but as an example, we are going to use the graph to manually, by hand, to find out the feasible region. I'm going to show you what the feasible region it is. It contains all the information above. Yeah, and then find out all the corner points, because according to the linear programming theory, the optimal solution happen in the corner points only. Yeah, and then the next step is, once we find out the feasible region and corner points, we are going to evaluate all the corner points using this objective function, and then it will tell you which one is the minimum or the maximum. So that is the next step. We are going to return the solution after evaluation. So this is an example. This example just a numerical example. Assume that we are going to do maximization. Okay, we can do minimization as well, but it depends on how we formulate the problem. Yeah. So again, just to remind you that when we multiply -1 to this function, we can turn the maximization problem into minimization problem. And so anyway, we are going to maximize z, and then so this z, that is 3x1 plus 5x2. That is, it means that if we are going to write it in vector form, that is what we have done before. x2, x1, x2, that is a linear function. Yeah, so you will just find out that linear programming problem. The cost is linear, and then subject to the constraint x1 less than 4, it is linear as well. All this constraint, they are linear function. If any one of them, they are non-linear, and then it is not a linear programming problem. We cannot solve the problem like this. For example, if we are going to have x1 squared less than 4, and then this is not a linear programming problem, we can use this method to solve it. Anyway, we are going to look at this constraint one by one. X1 less than 4, so that means this is this line. This is x1 less than 4. So this is x1 equal 4. And anything right here on the left, that would be satisfy this constraint, including negative region. Yeah. And then so we are going to look at another one, 2x2 less than 12. That is, when we use the equal sign, we can draw this line, and then anything less than 12, it means that anything below this line, yeah, including the negative right here. And then the same for this one, we are talking about this line. And x1 greater than 0, that means we are talking about this line on the right hand side. X2 okay, so and this is x2 greater than 0. Yeah, so x2, this axis is x1, this axis, that is x2. x2 greater than 0, that is, we are talking about this region. So anyway, when we combine all these 5 constraints, we just find out that this is the feasible region. Any point right here, it will satisfy these constraints. Now the problem is that we are going to find out one of this solution which will maximize this z value. Yeah. Okay. And now that is, I'm going to give you a little bit more idea about some definition or some terminology. Solution, it means that any point in this two-dimensional space. For example, this one, we call this is the solution to the cost function, but it doesn't mean that it is a feasible solution. When we talk about a feasible solution, it means that all these constraints are satisfied, and then infeasible solution, that is, at least one of these constraints, they are not satisfied. For example, if we are talking about a point right here, and then this is a feasible solution. If we are going to talk about a point right here, this is infeasible solution to this linear programming problem. And then the feasible region, that is the gray area right here, as I mentioned that within this region, any solution, any x will satisfy all the constraints. Optimal solution, that is, we are going to pick one that would maximize this cost function z. Constraint boundary, that is all this line. When we set the less than or equal to equal sign, and then we are able to construct all this line. They are the constraint boundary. Corner point solution, that is the point of intersection of all these constraint boundary. For example, A, B, C, D, E, F, G, H, and then you will just find out that they are the corner point solution. They are constructed by two boundary constraint boundary. Yeah. From A to E, because they are within the feasible region, and then we call this is the corner point feasible solution. Yeah, we call this is the corner point feasible solution. And F, G, H, they do not satisfy at least one of these constraints, and then we call this is the corner point infeasible solutions. Now we consider only two-dimensional space, that is, we only have two variables, x1, x2, and then so if we are going to extend it into n decision variable, and then that means the corner point, that would be the intercept of n constraint boundary, and then so we are able to define the constraint. But now this is the two-dimensional space, so when only two lines meet, and then we can find one corner point. So the corner point feasible solution are adjacent. It means that if they lie in the same segment, for example, this one, we have one constraint boundary, and then this is the adjacent. A to E, that is adjacent because it is in the same line. A and C, they're not adjacent because they are not in the same line segment. Yeah. Okay. So we have some more explanation right here, and then so we can also extend the two variables into n variables. Yeah. So n variables, if that corner point shared by n minus one constraint boundary, and then so that is the adjacent in the n-dimensional space. Yeah. So when we have two adjacent corner point visible solution, just like this, for example, AE, and then we call this is an edge. Yeah. So we have another edge, AB, BC, CD, DE. They are the edges of the visible region. And now what I have done, that is, in the beginning, I define the problem in this box and then graph the theory, graph the feasible region, and then that is the second step. The first step, that is, I'm going to find out all the corner points, yeah, A to A, B, C, D, E, F, G, H. Some of them, they're feasible solution. They are the corner point feasible solution. Some of them, they are the corner point invisible solution. And then the final step now I'm going to do, that is to do the evaluation and pick the optimal solution. Now, because according to the linear programming theorem, we will have the feasible solution at the corner point feasible solution, corner point feasible, I mean the corner point feasible solution, that is from A, B, C, D, E. We are going to pick the one which is able to maximize Z. Yeah. So we are going to ignore F, G, H because they do not satisfy at least one of these constraints. So using this table, I'm going to list A, that is 0, 0. So x1, that is 0, x2, that is 0. Corner point B, right here, x1, that is 0, x2, that is 6. So I'm going to put it right here, corresponding to each of this point. Plug it into this z value defined by the cost. That is right here. We just evaluate that. When x1, that is 0, x2, that is 0, and then the cost z, that is 0. We are going to do that for all these points. We just find out that point C, that is 36. That is the maximum value of z. So this is the solution that can maximize this value of z. That is the cost function subject to all these constraints. If you are going to find the minimum solution, and then that is fine, and then just pick the one of the value which give you the minimum value of z, and then 0, 0 will be the solution that minimize this cost function z. Yeah. Okay. And now take a look at this linear programming problem, as well as the way how do we solve it. It is very simple and easy to understand. Of course, we have some more complicated way to solve different variation of the linear programming problem. But anyway, I just demonstrate the basic concept. How do we solve that? And then if the problem that is simple, just like the example I just mentioned, it can be solved by paper in hand. Yeah. Of course, we can extend, or we can write some simple computer program which can help you to solve the solution. We can use the MATLAB or different kind of library. And another important thing, that is, up to now, we do not need to have any derivative information. That means we do not need to do df dx. Yeah. So that is, even though f is not differentiable, yeah, but we can still use the linear programming. But the thing is that if we call this is the linear programming problem and cost function, that is f equals cx, in that case df dx is always exists. Yeah, always exists. And we can also deal with the boundary, that is the constraint. Yeah, the disadvantage, that is, if we have many corner points, we have to examine one by one, because the corner point does not give you a clue of whether it is the global minimum or maximum. So we have to evaluate all the points, and it does not work well with the discrete variable. For example, if we are going to do integer programming, and then so this linear programming, it does not apply, but we can have another variation that is extend this to integer programming problem. And the cost function and constraint must be linear. If it is not linear, we cannot apply this method, as well as the coefficient, if that is the same as this one. Yeah. Sorry, I don't mean it is the same. What I mean that is the coefficient, it must be constant. If it is not a static problem, coefficient changing with time t, and then we cannot apply this method as